That's October 7, 2021, 5 p.m. So we are going to continue with apparent weight problems. Okay, it's apparent weight. Why do we call apparent weight? We call it apparent weight because depending on the circumstances, you feel lighter or heavier. That's why we call it apparent weight. Okay, it's not apparent mass. No, mass is always the same no matter where you are. Okay, but the weight may change. Your apparent weight may change. Everybody has had the experience in being inside an elevator, and when the elevator is about to move upwards, you feel a pressure in your foot, right? In your feet, right? If you had a scale right there at that spot, just like this guy has a scale here, you'd see the needle of the scale jumping up in value. Okay, well, when the elevator is at rest, the scale would indicate your weight. But the moment that the scale starts moving upwards from the bottom, you'd see the scale, the needle of the scale moving up a little bit and then stabilizing back in your regular weight. Okay, so that what your scale is showing there is not an anomaly. It's not an anomaly. It's an actual measurement. It is an actual measurement. The fact that the scale, the needle of the scale, jumped out to a heavier part in the dial, that's because your weight was apparently higher. You had a higher weight. You had a higher apparent weight at that small instant of time. Okay, those measurements are real. Okay, it's not that the scale is broken. No, no. The scale, and you can do the same thing. You know, you don't need to be in an elevator. You don't need to be in an elevator. You can do the same thing at home. Okay? You step in your bathroom scale, look at the recording, right? At the needle, and bend your knee downwards momentarily. What's going to happen? You know, when you are bending your knee downwards, initially you're moving downwards with your body, right? Your center of mass. You're accelerating from rest to a peak velocity. Make sense? So, somewhere in the middle of the trajectory, then you have to slow down because you cannot keep on accelerating forever downwards, right? Eventually you want to slow down and come to rest again. Make sense? So it's gonna be like that, you know? You go faster, 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 then you slow down, and come to rest. So you're accelerating downwards initially, at the middle of the way, then you start to accelerate upwards until you come to rest. Make sense? So what does your scale indicate during this maneuver of yours, during the time that you are bending your knees and going down? Again, you're not inside the elevator anymore. When you're going down, you're accelerating down, the scale is going to register a lower weight. Middle way, you start to accelerate upwards. Then the scale is going to indicate a higher weight. When you come to rest, the needle rests at your regular weight. Try to do this experiment. And you can do all the way around too. You can do, instead of bending the knees from upward, you can start with the knee bent and you move upwards. Make sense? If downwards, first the scale indicates low and then it indicates high and then goes to your normal weight, when you go all the way around, when you initially accelerated upwards, you're going to have the opposite indication of the scale. First, the scale is going to indicate a higher weight, then it's going to indicate a lower weight, and it's going to come to rest at their regular weight. You can do this experiment. It's very reproducible. I do that at home. Unfortunately, you don't have a bathroom scale here for you to see it right now. Okay? But you can even record it. You know, get your cell phone while you're doing those maneuvers, you know, bending the knees downwards and then repeat, you know, extending the knees upwards. Repeat the process. And it's very reproducible. Depending how fast you go down, how fast you go up, that's going to be the difference between your apparent weight and your regular weight. Okay? The difference between your apparent weight and regular weight is going to depend on the acceleration. Just by observing this difference, you can estimate what was your maximum acceleration. Just by estimating, just by recording the maximum difference in the weight, you can estimate what was your maximum acceleration during the bending and extending. Okay? But if you do that again, do in a step by step fashion. First, you go down and you stay down. Wait until the scale is stabilized, right? And now once the needle of the scale is stabilized, then you go up. Wait until the scale is stabilized and then repeat it. Okay? Go down, wait it, go up. And you're going to see that it's a repeatable experiment. Okay? When I was a kid there at home in Brazil, I didn't know those things, right? I was like 10 years old, 8 years old. And then we had those big scales there in Brazil. We had scales like those ones here. See that? Have you ever seen those scales, those big scales? We had those there in Brazil when I was growing up. And I didn't know how those scales would work, right? So whenever you're young, every kid is very active, right? You like to keep on jumping up and down and things like that, right? And then I would jump into the scale, and I keep on bending my knee up and down. I wouldn't stay steady, right? And then the needle of the scale keep on going up and down, up and down. I would turn to my mom, "Mom, the scale is broken. The scale is broken." "No, it's not broken." My mom would go, "No, you should stay steady here in the scale, and the needle of the scale is going to stabilize." My mom thought, that's how it works. Okay. So later on, I discovered that we can do those up and down maneuvers in the scale to learn about physics, right? So it's the same thing here. So let's solve this problem. You're going to see mathematically how it works, okay? Here you go. We did for the elevator at rest, we did the elevator moving at constant velocity, either up or down, it doesn't matter. Now let's do for the elevator moving upwards, with an acceleration, with an upward acceleration. It doesn't matter if the elevator is moving down, the velocity vector is down, it doesn't matter if the velocity is up. Okay? All it matters is the acceleration. Remember, Newton's second law of motion doesn't involve velocity. Newton's second law of motion involves acceleration. Net force is equal to mass times acceleration. There is no velocity there on the right side of the equation, right? There is no velocity in there. So here you go. I'm going to put the arrows for the acceleration here in this drawing. Here you go. I'm going to use this arrow here. In this case, because the velocity was greater than 0, that was the previous... What's going on here? Yeah, that was the previous example, right? Because the velocity was greater than 0, it means that the velocity is upwards. But the velocity is constant. Consequently, the acceleration is 0, right? Velocity constant. That was the last acceleration is 0. I'm going to emphasize it here. And then I'm going to copy this one and put the velocity downwards. Now the velocity is negative. Okay, acceleration is still 0. Because the velocity is negative, then the arrow of the acceleration is going to go down. Okay? Either way, you get your regular weight registered by the scale here. Either way. Now the thing becomes interesting when you have an acceleration. Okay, let's do acceleration upwards first. Right, acceleration upwards. And it doesn't matter if the velocity is downwards or upwards. It doesn't matter. You can have the velocity increasing upwards when the acceleration is upwards, or you can have the velocity decreasing if the vector velocity is downwards. Make sense? Okay? So you can have that. Here you go. If the velocity is upwards, if v is upwards, v increases, right? whenever the velocity and the acceleration has the same direction, the velocity is going to indicate, it is going to increase. And it's not going to affect your apparent weight whatsoever. Now, if the velocity was initially downwards, when the acceleration kicked in, I'm gonna go this way here. I don't want this one. I want the other one. Wait a minute. Yeah. I'm gonna put in the same drawing. That's what I'm doing here. If the x velocity is downwards, v now is going to decrease the speed, the magnitude of v. Let's put the magnitude here so there is no doubt that we are talking about the speed. Oops. V increases. Oops. Should have done that. Good. V constant less than 0. Yeah, I don't need that anymore. V downwards less than 0. V decreases. Oops. Oh gosh, I hate that. Good. V decreases. Okay, I'm gonna put a separate drawing. Right, and I don't need that. So you don't have too much stuff in the same drawing. It doesn't matter if it's one way or the other. The result is gonna be the same. Like that. Okay, so let's go take a look, because this is a Newton's law problem, we have to take a look at the forces that are being exerted in the subject. Here you go. We are going to have the weight, we are going to have the normal. The forces don't change. The forces don't change. The difference here is that the normal is in the direction of the acceleration. Do you see that? The normal is pointing in the same direction of the acceleration. So it means that the acceleration on the other side of the equation is going to have the same sign as the normal. Make sense? Okay, so let's go back to our equations. Here you go. That's the equation here that we did before. Apparent weight problem. Here you go. C, right? Acceleration upwards. Upwards. Here you go. F net is equal to weight plus normal. But it's the vector normal, it's the vector weight. And don't forget, now I'm going to put another vector here on the right side, which is the mass times vector acceleration. Newton's second law of motion. Okay? Now we have an acceleration. So what is in the right side is no longer 0. Okay, and then we are going to recognize that this is a one-dimensional problem, right? Let's go back here. This is a one-dimensional problem. The elevator is moving only in one dimension. There is no forces along the x and y axis, because this is a one-dimensional problem. I can here write this equation as a scalar equation. It's going to be minus mg. Do you see that? The normal is in the positive direction, so I can write down the normal vector with a magnitude around it. Oh god, this thing is gonna make me sleep. No, it's not this one. And I clicked the wrong one. Oh boy. I need to buy a new one. This one is just 2 years old. It's not supposed to be working like that. Here you go. And I can do the same for the acceleration. Right? Here you go. I put the magnitude there just to emphasize that we have a positive quantity. Okay? See, the normal has the same sign as the acceleration, right? I'm gonna put a plus here so you have the same sign as the acceleration because they're in the same direction. They have the same sign because they're in the same direction. Look at the drawing. Normal, same direction as the acceleration. Okay, and same. You could have rewritten that in the other way too. Okay, you could have rewritten that like that. Multiply both sides by -1, and the acceleration on the right side we're still gonna have the same sign as the normal. Okay, here you go. Right? It should have the same sign. But what we want to do, we want to find the normal, right? Every time that you see a problem on apparent weight, you know, like I told you, it's the secret, right? The secret of the most close guarded secret in physics. What is the scale indicates? It's not necessarily your weight. What the scale registers is in reality the normal force that you apply to the scale. Okay? So that's the most closed guarded secret in physics. The scale doesn't indicate your normal. The scale does not indicate your weight. The scale indicates the normal. And depending on the circumstances, the normal may or may not coincide with your weight, with your normal weight, depending on the circumstances. Okay? So here we go. Let's solve now for the normal. I'll get this guy here. I will. I'm gonna pass the mg to the other side. You're gonna change the sign of mg because it was negative on the left side, becomes positive on the right side, and bingo! What happens? Your normal is gonna be the weight plus something else, plus a positive quantity. Your apparent weight now is heavier. You're feeling heavier. Okay? When the elevator starts moving, accelerating upwards, not moving, but accelerating upwards, that would be more precise way of, you feel a little bit heavier. And that's something we all experiment in real life. Okay? The normal is greater than mg. That's the conclusion here. Your apparent weight is more, greater than mg. So stop to consider that, absorb it, right? Distill it. It all comes from the equations. So now I can draw here this guy. Watch the scale indication here, right? Is the scale indication correct compared to this other drawing here, the previous one? Is the scale indication correct in my drawing? Yes or no? Huh? See, the scale indication is right in here. The needle of the scale. Is it correct or not? No, it's not, right? So I'm going to make it more realistic by changing the indication here. Better now? Okay, now we can see it, right? Now it's more realistic, right? Moving with constant velocity, accelerated upwards. Constant velocity, accelerated upwards. Okay, and then the next drawing is going to be with accelerated upwards but moving downwards. It's still the same situation, right? I will erase this one here and this one and paste it. V decreases. V decreases because the acceleration is down, is upwards, is contrary to the velocity vector. Okay, so here you go. Watch the scale indication. Okay. How fast does the elevator have to move for you to have half of your apparent weight? You know, let's numerical example. How fast? No, not how fast. What must be the acceleration? What must be the acceleration of the elevator for your apparent weight indication be half of your actual weight indication? Okay. What must be the acceleration of the elevator for your apparent weight indication to be half of your actual weight? Look at the equation and tell me, hey, wait a minute, no, sorry. What must be the acceleration for your apparent weight indication to be twice your actual weight, right? Twice your actual weight. Look at the equation and answer. Can you picture that? Think about that. Must be G plus A. G plus A must be twice G. So you can get 2mg here, right? So the acceleration is supposed to be what? Okay, here you go. Let's do the solution. I want to put solution here. Solution. Your apparent weight must be 2 mg. Must be 2 mg, right? So here you go. N is your apparent weight. Okay. N must be equal to 2 mg. 2 mg. And I'll solve this equation for A. I'm going to cancel M with M. I don't need the N anymore. on the equation. I don't need the parentheses anymore. So for A, what must be the acceleration? Here go. This G goes to the left side with a opposite sign, and then you get what? You get the acceleration must be G. Okay, that's the type of situation that test pilots call I'm pulling a 2G maneuver. Have you ever heard of that? I'm pulling a 2G maneuver, I'm pulling a 3G maneuver, 4G maneuver. Okay? The acceleration is G upwards. It sums with the G of the acceleration of gravity, becomes 2G. Okay? So if you're in a rocket, just like an astronaut, the rocket is propelling you at an acceleration of 10 meters per second square upwards, you're going to feel twice your weight. Okay? 20 meters per second square, you're going to feel 3 times your weight. Okay? 30 meters per second square, 4 times your weight, and so on. Okay? 4 meters per second square, 5 Gs. I have already felt 5 Gs. If you go in those roller coaster, you know, you have seen, everybody has rode those roller coaster there in, what's the name, Six Flags, right? I went with my students there, with my LA Harbor students there. There's the Superman ride. Have you taken this ride at Six Flags? How many G's is the Superman flag? Is Superman ride? Huh? How many G's? Do you know? 6 G's. Momentarily. In a fraction of a second. Okay, I felt it. I felt it. My student that was next to me, they were impressed too. Man, how many G's is that, you know? They were asking me. Yeah, but it's very short, it's very small amount of time, like a tenth of a second. Okay, you cannot sustain very high levels of acceleration in those rides. You can sustain high levels of acceleration for a longer time in an airplane. That you can do. Okay, in an airplane you can. So sometimes I used to practice aerobatic maneuvers. I could feel 5Gs in my airplane because I was pulling my airplane very hard. You know, I was not going up, I was not going down. I was actually describing a circular trajectory. You can also, you know, at the bottom of the circular trajectory, the airplane has the centripetal acceleration pointing upwards. Make sense? Depending how fast you are going, and that's going to be the next problem they're going to be solving. You can get 5Gs with your airplane. Just pull up on the yoke of the airplane very fast. Make sure you don't exceed the limitations of the airplane, of course, because you don't want to fly without a wing, right? If you exceed the acceleration limitations of the airplane, the wings can break down in flight, separate from the airplane. That can happen if you're not careful. Okay, did you get the idea? So here you go. Let's do now for the next one. Okay, so velocity down. Here you go. Velocity upward, velocity downward. It's applicable either way. The only thing that you have to worry is the direction of the acceleration vector. I don't need that anymore. I'm going to erase that. Okay, now we're going to do for the next one. Acceleration downwards. All I have to do here is copy those two drawings and invert the direction of my acceleration vector. Here you go. Now the acceleration is going to be downwards. Here you go, right in here. Okay, whether the velocity is up, the forces remain the same. The forces remain the same. There's no other force applied to our test pilot here. Here you go. Okay, whether the velocity is upwards or downwards, the filling, the apparent weight is going to be the same. And let's see what's that. Here you go. The way we do it, normal minus weight, right, is going to be equal to ma. Or if you write down in the vectorial format, let's write down in the vectorial format now. Here you go, acceleration downwards. I'm going to copy that. And here we go. And then we're going to do a numerical example as well. Here we go, d acceleration upwards, now it's acceleration downwards. Okay? This equation doesn't change because it's a vectorial equation. This equation doesn't change. This left side of the equation doesn't change either because the weight is still down and the normal is still up. But the right side is going to change because the acceleration is downwards. Okay? The acceleration is downwards in the same direction as the weight. See that? Here you go. Sign of the weight is the same sign of the acceleration. Okay? And here you go. If we multiply both sides by -1, the acceleration still have the same sign of the weight. Okay? That's the trick that you gotta keep in mind. If the acceleration is the same direction as the weight, then they must have the same signs in the equation. If the acceleration is in the same direction as the normal, then both must have the same sign, right? So let's continue. What we're gonna do, you wanna solve for n, and look what we're gonna get. We're gonna get minus mg, no, plus mg minus ma on the other side, and g minus a. And what does it tell us? Your apparent weight is going to be less than mg up to a certain point. Okay? Up to a certain point. You know, it's going to be less than mg provided, let's see, g minus a is, you know, it's greater than 0. Let's see how we're going to do that. I'm going to do this way. Is greater than 0, less than 1, right? There's a point in which the normal ends up being greater than mg, even under these circumstances. Okay? Even under these circumstances. Numerical example. What must be the acceleration of the elevator for your apparent weight indication to be 0? Now, you know what? To be not 0, but to be half your actual weight. Numerical example. Okay, think about that. Half your weight is mg divided by 2, right? Any questions? Don't forget, here go the equation that we have to use is this one right in here. N now is no longer 2mg, and now is mg divided by 2. And we must have a negative sign here. We solve this equation. divided by 2. M cancel is M. And we solve. Let's see, I'm gonna put that minus here. So I do this step by step, right? And then, so if your elevator is accelerated downwards at 5 meters per second square, your scale is going to indicate half your weight, half your regular weight. It's going to be something like that. Oops, too much. Okay, here you go. Okay, so less weight. There is a special case in which you're going to become weightless. There's a special case in which you can become weightless. Okay, so let's do this example as well. Here you go. Numerical example. Under what conditions what must be the acceleration of the elevator for your apparent weight indication to be 0? Weightless. 0. Or weightless. Okay? Your apparent weight must be 0. Your normal must be 0. Okay? You go. You gotta be 0 here. That's gonna be 0 here. Okay, that's gonna be 0 here. And that's gonna be acceleration must be equal to g. Okay? So whenever your elevator is going down, whenever your elevator is in free fall, you cut the cable of the elevator, just like you see in those movies out there, right? You cut the cable of the elevator and everybody floats inside the elevator momentarily. We experienced that in the parks as well. Okay, and that's gonna be the indication of the. And if you manage, right? If you manage to accelerate fast enough downward with your knees, I don't think you can do that. At 10 meters per second square, your scale is going to indicate 0 momentarily. Try to do that. See if you can do that at home. Bend your knee fast enough to show an apparent weight equal to 0. I don't think you'll be able to do that. Okay? It's very difficult to achieve 10 meters per second square with your knee, but just by bending your knee. Okay, so one more. Let's see, apparent weight. And then there is one more interesting situation that is illustrated right in here. Right here in this case. Okay? In this situation, all you have to do is to cut the cable of the elevator and let the elevator fall, free fall. But to do something like that, you have to do more. Not only you have to cut the cable of the elevator, but you have to install rocket engines at the top of the elevator. You see the rocket engines here? In this case, the rocket engines are here to ensure that the elevator is going to descend at an acceleration greater than 10 meters per second square. Let's say 20 meters per second square. Okay, 20 meters per second square, and we can solve that in the equation. Then what happens here? At 20 meters per second square, you're going to hit your head here in the ceiling of the elevator. It is as though you'd be upside down. Look at the hair of the guy. I made sure my drawing, the guy who did this drawing for me would put his hair in this way. That's what we call negative G. The blood rushes to your head. And it's not just that. The scale is indicating a negative weight. 0 is here. See the indication here of the scale? It's a negative. Minus 20, minus 40, minus 80. Okay? And this guy here, what's happening to this guy? You know? He
Gaining weight. I mean, he's pushing weight to the to the scale.
yeah, that's right. It is he's capable of walking upside down if you have a situation like that. If you accelerate your elevator, 20 meters per second square downwards, you will be able to walk in the ceiling of the elevator until, of course, the elevator hits the ground, right? And then nobody's gonna tell the story anymore. Okay? There is a limitation, right? How long you can do that. You can do that as an airplane too, right? You can do that with an airplane at the top of a parabola. Make sure you're flying, put the airplane pointed upwards and go down with the yoke very fast. Okay? Go down with the yoke very fast so the trajectory, the acceleration, the centripetal acceleration at the top of the parabola is more than the acceleration of gravity. You can do that as an airplane, you can do that as an airplane too. Okay, in this case, the centripetal acceleration of the airplane should be 10 meters per second square. In the other case, the centripetal acceleration of the airplane must be 20 meters per second square. The parabola has to be even steeper, right? Yeah.
What if the plane at the top of the parabola continued to make a circle?
Oh, then we're going to discuss that too in the next chapter, right? Let me. Remember, it has everything to do with the acceleration, with the vector acceleration, right? Let me make a drawing here for you so you can understand. It's not something. Let's see here. I found it. Yeah, here you go. So here you go. We're just talking about one-dimensional motion, right? Here you go. Here's the elevator, right? Here you go. Individual in the elevator. Acceleration down, right? Lower weight, right? Lower weight. Acceleration up, higher weight. Okay, acceleration down, from let's see, how much would that be? A between. Oh gosh, no, give. I'm getting tired already. Uh, A greater than 0, less than 20 meters per second square. Okay? Okay? But now, if you go ahead, the acceleration now is greater than 20 meters per second square, it's going to be higher weight. Higher weight, upside down. Upside down. Right? Let's see, I can go up to 10. Okay? Up to 10 here, lower weight. So I'm going to do another one. Let me do another. I don't have my eraser here. Well, I'll have to erase with my hand. Okay, so let's do this way. Lower weight, right? You go, and here you go. Between acceleration down, A greater than 10, less than 20, downwards, is still lower weight. Okay? Still lower weight, but you're going to be upside down. Okay?
Professor, is that me erasing there? I can't see too well from here. But I think that might be one.
Oh, thank you. Yeah. Thank you. I didn't see that. Okay, you got that, right? Here you go. We also have that other situation. Here you go. Individual here. Acceleration upwards. No matter what the value of A, higher weight. Higher, I'm talking about apparent weight, okay? Higher apparent weight. Higher apparent weight. We start with this one, and then we start looking at this one. And then we finally have this other situation, right? Negative weight again. And you folks gotta be careful with negative weight. You fly an airplane, aerobatic maneuver. Accelerations greater than 20 meters per second square. Higher weight, upside down, upside down. Four situations. Okay, four situations that you can have. Greater weights upright, lower weight upward upright, lower weight upside down, higher weight upside down. It all depends on the value of the acceleration. Okay, that's a summary of the equations of the equation that we got here. Let's see if I have it. Oh, here you go. I have the vectors here. V equal to 0, V equal to constant, acceleration constant upwards. Let me see, I didn't change the indication of the scale. Okay. Yeah, I didn't change the indication of the scale. What time? That's 5:47. We're getting to the point where we need to take a break. Let me take attendance first. Any questions about that? Attendance. And like I said, those things we can experiment in an airplane. NASA has an airplane, an aircraft. You must have heard about that, right? Have you heard of the Vomit Comet? Yeah. So NASA has this airplane that they use to train astronauts. So they fly the airplane in such a way to produce different levels of apparent weight. Different levels of apparent weight. Okay? Most of the time, the airplane is flown to simulate the zero gravity of space to train the astronauts. And they also use this airplane to perform experiments in microgravity. And I was lucky enough to participate of some of those flights when I was working at NASA. Okay, and then I went like for 120 parabolas with the airplane. Okay, so the airplane is flown up like in a roller coaster profile, right? At the top of the trajectory, you feel lighter. At the bottom of the trajectory, you feel heavier. So it's an alternation of 2G maneuver at the bottom and 1G maneuver and 0G maneuver at the top. So they go just like that, back and forth, back and forth, back and forth. Okay? Those flights last like 2 hours. They do like something around like 40 parabolas during a 2 hour flight. They have videos there in their site, okay? In the NASA site about that. Today is the 7th. They usually take students in those flights, okay? NASA has a program to take students to perform experiments in those flights. Daniel Abraham, are you there? Nope. Mario Acevedo. Next, Haron Atif. Okay. Musa. Genesis Bell. Nope. Jennifer Camarillo. Nope. Vincent D'Aloisio. Okay. Robert Faust.
Here.
Pedro Flores. Lawrence Flores.
Here.
Alexander Garcia. Sung. Brian Herrera. Nope. Brian Inez. Athena. There. Okay. Jesus Lap. Nope. Cassandra. Dylan Martinez. Henry Martinez. Nope. Leonardo Melgar. Rafael Mercado. Raymond Miramontes. Jaime Mondragon. Alexis Negret. Yahia Paris. Stop coming. Right. Who's trying to add Jensen Marantoni? Is he or she here? Yeah, he came one day, but then he didn't show up anymore. Anybody knows this guy? He talked to me once. He was trying to add. Okay. Marco Antonio Partida. Armando Pérez. Abraham Pérez. Nicholas. Hans. Hans Puskar. No. Ramon Quintana. Albert Ramirez. Ali. Nope. Amna Sieda. Stop coming, right? Dave Sompaxley. Nope. Sieda. Antonio Vega. Kenneth Villagomez. Nope. Patrick Villavazov. Nope. And Nolan Williams. Okay, 25. I guess those students decide to stay at home so they can study for the exam, right? What time is that? 5:52. 5:53 now. 15 minutes break. 8:608. I'll see you in 15 minutes. Okay, here's an updated version of the syllabus, of the schedule of the syllabus. Okay, so version number 6. We're falling a little bit behind with respect to the original schedule, but that's okay. Again, exam today, chapter 1 through 4, opens at 7 p.m., close at today, close at 7 p.m. tomorrow. Okay, so going back here to my notes. Laws of motion, applications of Newton's law. So what we did so far here. What we did so far was to apply Newton's law of motion to 1D motion. Now we will apply it to 2D motion. Specifically, in the case of circular motion. That's the whole idea. Okay, so circular motion. Okay? So what you have to know about circular motion is that, let's start with uniform circular motion, okay? Let's put it this way. First, uniform circular motion. And then later on, non-uniform later. Then non-uniform circular motion. Okay? Okay, Newton's laws relate the net force to the acceleration. In uniform circular motion, the acceleration that we have is the centripetal acceleration, right? That is which is the term that's going to go, which is the term that is going to go in the right side of Newton's law, of Newton's second law. Okay? That's what you have to keep in mind. Remember, it's a vectorial equation, it's not a scalar equation. And the centripetal acceleration is also a vector. It's a vector that points towards the center of the circle. Right? So let's go back to Newton's second law of motion. Let me see if I can find it. Right in here. Newton's second law of motion. It doesn't matter if it's a Cartesian coordinate system, it doesn't matter if it's polar coordinate system, it doesn't matter if it's spherical coordinate systems. Doesn't matter if it's elliptical coordinate system. Have you ever studied elliptical coordinate systems? They do have it there, out there, believe it or not. Okay? We don't study it here at the undergraduate work, but there are. Okay? It doesn't matter. All it matters is a vector. The vector doesn't have to be necessarily a vector in the Cartesian coordinate system. It can be in any coordinate system. If it's the circular coordinate system, then we'll be talking about the polar coordinate system. Okay, it's a circular in the 2D plane, is a polar coordinate system. So we use, okay, in a circular coordinates, for circular motion, for uniform circular motion, we have only the centripetal acceleration. Consequently, the above equation becomes, here you go, mass times acceleration, and the acceleration is going to be centripetal acceleration. Centripetal equal. Okay? So let me see if I can show you the illustration. Right in here. See that? We looked at that before, right? Uniform circular motion. We know the velocity. Let's say we know the velocity. We know, let's see, we know the radius. We know the mass. Let me see what this is. This is an illustration of a problem. Okay. Yeah, here you go. Those are all vectors, right? All the mass is not a vector, of course. What? Okay. The force, the net force, ends up being a centripetal force. Okay. In order to satisfy the fact that we have a centripetal acceleration, The net force will also be a centripetal force. And I'm even going to write that down here. Here you go. Here you go. If the net force is not a centripetal force, then you do not have a uniform circular motion. Okay? For uniform circular motion, the net force must be a centripetal force, must be pointing towards the center of the circle. Otherwise, you do not have a uniform circular motion. All right, here you go, centripetal force, centripetal acceleration, here you go. I'm going to do 2 slides here, like that, here you go. Net force points towards the center. Okay. And if it's uniform circular motion, the net force is going to be a centripetal force. It's going to be pointing towards the center. You know, maybe the particle is subjected to more than one force, maybe. But the net force is still going to point towards the center of the circle. Okay? That's what you have to consider when you solve those problems. Let's take a look here at my notes. Here you go. For the above particle, the net force can be written. Oh, here you go. I'm going to see here. Yeah, I'm going to replace this drawing with a better one that I have here. Here you go. So my notes look nicer. Snipping tool. It was a student who told me about this software. It's really nice. I like it. The snipping tool. Have you ever used that before? Anybody here? I really like it. It's very convenient. Here we go. Center of the circle. Here we go. You know what? I don't like that. I'm gonna get just the circle and I'll get the X and Y. Here you go. Can do better than that. Okay. Here you go. Undergoing uniform circular motion. Okay. For example, we have this example here. Okay, it's and by the way, we are going to have a lab with uniform circular motion. Okay, we are going to do a lab on uniform circular motion in which we are going to verify this relation that you see right in here. Mathematically speaking, you know, Hegel, the centripetal acceleration can be written in this way. We saw that before, right? V squared over r in the negative radial direction. That's the positive radial direction. That's the negative radial direction. Is the x hat cosine of theta minus x, let's see, is the minus x, let me see here. The r vector is, yeah, the r hat vector is cosine of theta in the x hat direction plus sine of theta in the y hat direction. Is a plus sign. centripetal acceleration has minus signs on both the sine and the cosine, right? But then, you know that cosine theta x hat plus sine theta x hat can be written down as a single vector, which is r hat. Okay, simplifies the notation. Now let's do this example. This example is the conical pendulum. This is a type of motion that I would like to implement a lab one day. You know, we have equipment to implement this type of motion in the lab. I haven't time to come up. I haven't had time yet to do that, but in the future, I plan to implement a lab based on this type of motion. Let's take a quick look at the conical pendulum. Okay, some time ago I started looking at the conical pendulum, and why they throw those problems at us at us in the class, but they don't explain why they do that. Okay, well, they do that because there is some practical applications on the conical pendulum. Right? Let's see if there is. What's the practical application for the conical pendulum we have? Here you go. I remember reading about that before. Here you go. Wikipedia, right? Let's go to Wikipedia. At my time, we would go to Barça or Encyclopedia Britannica, right? At the time that we didn't have internet. Conical pendulum consists of a weight bob fixed at one end, string rods. Blah, blah. Let's see, uses. Analysis, here we go. During the 1800s, conical pendulums were used as a timekeeping element in a few clockworks timing mechanisms. That's the practical application of the conical pendulum. You have the regular pendulum, right? That moves just in the XY plane, which has timekeeping applications. And in the 1800s, they start using the conical pendulum. The pendulum started to be used back at the time of Galileo Galilei. Okay, he was the one who described for the first time, who documented for the first time, the fact that the chandeliers of his church would describe a type of motion that could be used in timekeeping devices. Okay? So Galileo Galilei, he is an interesting story. Okay, it's out there in the Wikipedia. We keep on discovering those things every now and then. Wikipedia is really nice. I like it. So Galileo Galilei, when he came to this realization that we could use a pendulum as an element of a timekeeping device, he started working on that. At that time of Galileo, they had mechanical clocks. They had mechanical timekeeping devices, but they were not based on pendulum. They were based on something else. Okay? And so Galileo Galilei started working. He was already at the end of his life. He was blind. He couldn't do the experiments, and so he approached his son. Okay, why don't you help me build this timekeeping device based on pendulum, right? It was the last year of his life that Galileo approached his son, right? And they start working on the device, try to improve a mechanical clock. Galileo Galilei died, didn't see the pendulum-based clock built. His son continued his work, but then his son died too. And he couldn't finish. The Galileo Galilei family couldn't finish the mechanical pendulum clock timekeeping device. Okay, so it ended up being someone else who came up with the timekeeping device based on the pendulum. It was Huygens, Christian Huygens. Have you heard of him? Christian Huygens. Okay, and here Wikipedia has a beautiful story about him. You know, he managed to build a mechanical timekeeping device based on the pendulum. The device was so good, but so good, that it was 60 times more precise than the timekeeping devices of the time. 60. We're not talking about 10 times, we're not talking about 2 times, we're not talking about 30 times, we're talking about 60 times better than what they used to have at the time. That's what we call a quantum leap in improvement. Okay? That's what we call, and Wikipedia tells the whole story right in here, Christian Huygens. So if you're going to, one day you folks are going to invent stuff new, this stuff, you're going to patent stuff, you're going to try to improve technology. If you invent something that's twice better than what we have, forget it. It's not going to make it. Nobody wants to hear about a device that's twice better or twice cheaper than what's available out there. They want to hear about a device that's at least 10 times cheaper. And if it's 100 times cheaper, 100 times better, then they will put money on you. Okay? That's how it works in real life. Believe me. No, don't bother about twice better, 3 times better, maybe 10 times, yeah, 10 times better, they will pay attention to you. But Christian Huygens, that's what he did. He came up with a mechanical clock that was 60 times more precise than any available clock at the time. And then what else did he do? What Christian Huygens did? He used the pendulum. He figured out a way to interface his pendulum, his mechanical device, to existing clocks that were already built. He retrofitted clocks that were available already in the market with his pendulum. So being 60 times better, it was not enough yet, okay? So he had also to figure out how to use his pendulum in conjunction with existing devices, okay? So they wouldn't throw away the existing devices. Makes sense, okay? If you're going to invent a better engine, okay, for your car today, make sure you invent a better engine so you can retrofit existing engines. Don't throw away existing engines. Figure out a way to make your engine better so you can retrofit what exists out there, okay? That's how it works in invention, okay? Maybe you get something really good and you can throw away all that stuff, but if you want a smooth going road, you gotta figure out a way to interface your invention to existing inventions. Okay, so here you go. Dutch scientist Christian Huygens. See that? In 1673, that was the regular pendulum. That was not the conical pendulum. In 1673, Dutch calculated its period. Let me see here. The conical pendulum was first studied by English scientist Robert Hooke. Okay, he was first studied by Robert Hooke. Okay, as a model of the orbital motion of the planet. Calculate. Okay, so what happened here? Christian Huygens, not only he invented a pendulum that a timekeeping device that used a pendulum that moved in this XY direction, but he also studied the conical pendulum. Okay, that's what he's saying here. He was not the first one. It was Robert Hooke who first studied the conical pendulum. And think about it. The conical pendulum is something that moves like that. Okay, that's what the conical pendulum is all about. The regular pendulum is this one here. Okay, we are trying to solve this type of problem, which involves uniform circular motion. Okay, so think about that. Back in the 1600s, Christian Huygens invented a better timekeeping device based on the regular pendulum that oscillates in the XY plane of coordinates. He also studied the conical pendulum, but he didn't put it to practice. Okay. Later, it was used as a timekeeping element in a mechanical of clocks and other clockwork timing devices. Okay, and but it was during the 1800s. Christian Huygens studied this type of pendulum back in the 1600s, and it was used only in the 1800s in practical devices. Were used as the timekeeping element in a few clockwork timing mechanisms, where a smooth motion was required, as opposed to an unavoidably jerky motion provided by ordinary pendulums. Two examples were mechanisms to turn the lenses of lighthouses to sweep their beams across the sea. Okay, can you picture that, lighthouses? You have this beam of light that must be swept around, right? And apparently they use the conical pendulum to do that. And the location drives of equatorial Mount telescopes as well. Okay. To allow the telescope to follow stars smoothly across the sky as the Earth turns. Okay, so that's one of the applications of the conical pendulum. Two applications. two clocks, and also no, actually 3 applications, right? One as a timekeeping element of a few clockworks, another one to turn the mechanism of lighthouses, and a third one is in the mechanism of equatorial mount of telescopes. At least 3 applications. One of the most important uses of a conical pendulum was the flyby governor, centrifugal governor. Let's see, invented by James Watt. Do you remember James Watt? Who was James Watt? James Watt. Anybody knows about James Watt? When does the Industrial Revolution started? Huh? No. So just earlier. Take a look. This guy played an important part in the Industrial Revolution with the invention of the steam engine. It was in the late 1700s. That's when the Industrial Revolution started. Okay, the England, right, was the first country who started the Industrial Revolution. Then other countries followed afterwards. Okay, and it was James Watt himself that had a very important contribution to the Industrial Revolution with the invention of the steam engine, which is an internal combustion engine. Okay, and so he used a conical pendulum as the centrifugal governor of engines. Governor is a type of device that's used in engines, okay? I studied that stuff in the engines when I was doing my commercial pilot license. I had to learn about this device called the governor that controls the output of an engine. Okay, that's what the governor is all about. Okay, so 4 important inventions, right? Steam age in the 1800s, okay? Regulate the speed of steam engines during the steam age in the 1800s. The playground game tetherball uses a ball attached to a pole by a cord. Okay, so some amusement park rides act as a conical pendulum, okay? So we have all those applications here. Just as a little background, what the conical pendulum is all about. Okay? They ask you to study that, but there is a reason why they ask you to study, because it has practical applications, right? In the past, at least. Maybe you don't use that anymore, but... So what is this example is all about? There's a particle of mass m suspended by a string of length L. The particle moves with constant speed v in a horizontal circle of radius r. Here you go. That's the circle here that is describing. Find the tension applied to the string and the velocity in terms of the other parameters. You do not know v, you know m, you know L, you know r. Okay? Find the tension to the string and v in terms of the other parameters. So you're going to apply Newton's second law to this configuration that you see right in here. Let's do that together. It's a string, right? Let's see if I can picture that for you. Okay, let's see here. Here you go, a string. Here's a bob, and that's a conical pendulum. Okay? Conical pendulum. Undergoing uniform circular. Somehow it undergoes uniform circular motion. Most likely it has some sort of propulsion here too. And that's a type of motion that we can reproduce with some equipment that we have upstairs in there. Okay? I have been thinking how we can implement a conical pendulum in the lab so you can learn about it. So let's do the math. Here you go. Do the drawing, right? Identify the forces. Okay, this bob is suspended. There is no surface touching the bob. Okay, it's suspended. Suspended, okay? Here you go. Like that. So you have just the weight and the tension. The tension ensures that the object doesn't fall down to the ground. Those are the 2 forces. Most problems in physics, I would say every problem in physics, it's very crucial that you draw the situation and find the forces. Okay, don't try to solve a problem in physics without making drawings, and that's a very useful skill, okay, to capture in image what was described to you in words. And it's very difficult too, it's a very difficult skill to acquire. Don't think it's easy. Let me see if I have a better drawing here. Next one. Here you go. Uniform circular motion. We are going to have a net. See, we have a force. Let's see here. Here you go. We have the tension. I'm going to do it step by step here. Uh-oh. What's going on here? Huh. Okay, I'm going to do it step by step here. First, the weight, right? And then the tension. And then the tension. First the weight. And then the tension. Remember that I told you, the individual forces do not necessarily point towards the center, right? It is circular motion in this plane, but the individual forces do not necessarily point towards the center. But the net force does. The net force points towards the center. Why is that? The vertical component of the tension is canceling out the weight. And the only thing that's left is the horizontal component of the tension that's pointing towards the center. Do you see that happening here? The particle is undergoing uniform circular motion because that component of the tension is pointing towards the center. Consequently, we have a centripetal acceleration. I'm going to draw this net force. Let's put it this way. Here you go. I'm going to do this way. I'm going to do the following way to make it nicer. Here you go. I'm going to dash those two like that to emphasize that the net force is towards the center. Let's see, this one here better, right? Here you go. And now I'm going to copy this solid arrow here and project along the horizontal direction. Make sense? That's the net force. What you see here is the x component of the tension, but it is also the net force. Okay? There is no other force there. And I'm going to change the color to red. Yeah, like that. I'm going to go back here in the other, here you go, this one. I'm going to copy and paste. We're running out of time, right? 6:41. Here you go. Net force is equal to the centripetal force, and even better, I'm gonna go further than that. It's equal to the horizontal component of the tension. Okay? This one, here you go. And I'm gonna put everything in red, so those red quantities is associated with the red arrow. Okay? Make sense? What time is that? 6:42. Oh, let's stop here, right? So you have time to go back home and start the exam. And then next time we pick up on that again. I'm gonna erase this guy. Save it. I got the Armando, I got the email.
The email?
I got.
Okay.
Okay. So, but come back. They told me that it should be 3 hours, okay? Not two, not four.
No, oh, okay. So
They wrote down 150% there.
that's perfect.
Okay.
Yeah. Okay.
Bro, I got a
Thank
quick
you.
question. Once we're done with the exam, so do we have time to turn it in, or we're gonna have to turn in during our time of the exam?
Well, it's submit every single line. You have 2 hours to submit it
So including submitting.
automatically. You submit automatically.
Oh, okay. So once I'm
If you
done.
don't submit it, the system is gonna submit for you automatically.
Okay. So is it? So when I take the exam, I'm gonna. It's multiple choice, or how do I'm
It's
not
going
sure.
numerical, just like the yeah. It's not multiple choice. It's numerical,
But like the homework.
like the homework
Oh,
in WebAssign. Yeah.
okay. Okay. Just
Some
wanted to make
homework
sure.
in
I was kind of
WebAssign are
worried.
multiple choice, right? But this one is just numerical.
Because I was kind of worried too, because I had never done this before, and I was wondering. I was like, is it gonna be like, we're gonna have enough time? So once like say I'm almost finished with the exam and it's already 2 hours, it will just submit.
Yeah, yeah. I believe I haven't taken the exam myself, so I do not know how it works. Okay,
Okay.
but I believe there must be I never had any problems. The students always, did well. I believe that there is a button for you to submit it.
Okay.
But if there is not a button, it submits to you automatically
Okay. Just wanted to make
at
sure.
the end of 2 hours. Yeah.
Yeah. Okay. Okay, bro.
Okay.
Thank you.
Yeah.
Have a good night.
You too.
Thank you.
Cancel. Ver. Conical pendulum. Nope.